Okay, in this video, we want to start the chapter on sets. And sets or set theory is something we've already been using to some degree, but we want to be more careful about describing what it is. And set theory is the foundation of all of mathematics. So it's very important to be able to work with sets, to be able to basically take any higher level math course. And just to start out with some examples, there are the natural numbers, which is like the set 1, 2, 3, 4. By the way, there's a little bit of a convention here that we need to be careful about. The book that I'm using for this class does not include 0 in the natural numbers, but other classes will. And so anyway, there's just not a universal agreement here. And so just you should know that in some classes, 0 might be in the natural numbers. In any case, for this class, we're going to use the natural numbers to be these numbers. I've already told you what the integers are. So they are, basically we add in the negative numbers. So this is the integers. And another symbol I'll introduce right off the bat is what's called the empty set, which is just the set with nothing in it. And this is really just helpful for us, really just for communicating when we will get the empty set sometimes after doing a set operation. Okay, but that's just 3 examples of sets. Sets in general are just any collection of objects, and we'll always use these curly brackets to denote a collection of objects, right? So some examples could be the collection of odd natural numbers. That's a set. It could just be a finite set like this. This has 4 elements in it. Could be like multiples of 3. And a set could be a collection of sets itself. So it could be like the set containing the set comma 1 comma 2, containing the set 2 3, containing the set 3 4. And we could do something like set containing the empty set, and then the set containing the empty set, and then the set containing the empty set, and the set containing the empty set, so on and so forth. I'll just stop there. Anyway, those are some examples of sets. Now, oftentimes I'm going to want to visualize a set to some degree. So a lot of times I will visualize it by just creating a circle of some sort, which is just supposed to somehow encompass the set in a picture. So for instance, here is a picture of a set that I might use to visualize something. And these visuals are just supposed to communicate some intuition, but we'll always give a rigorous definition for anything that we need to be rigorous about. But oftentimes I will also draw some kind of picture to help us understand the idea. Okay. So anyway, we can always define a set by just listing out, or one way of defining a set is by listing out the elements in that set. But it turns out that that is a little bit limiting. So we need another way of defining sets, and that's what's called set builder notation. Okay, so we want to talk about set builder notation. And basically, it's either that we don't want to list all the elements out, or sometimes it's because we cannot list all the elements out. And so instead, we're going to do it like we're going to make a set the following way. It's going to be some elements. This is just a general description. I'll give you some examples. So we're going to describe elements somehow, and then some condition used to generate elements. But really, you need some examples to see what I'm talking about. So here's an example. So I might say the set of all elements 2 times n, where n is an natural number. Or I could say the set of all elements of the form 2m plus 1, where again n is a natural number. Other examples could be set of all numbers that can be written as n squared, where n is a natural number, or set of all integers where n is even, is another way of saying this. Okay, so what are these sets if I wanted to list them out? Just to make sure we understand what the set builder notation is saying. Here, that means it's like 2, 4, 6, 8, 10, so on and so forth, right? The set of even natural numbers. Here we're looking at 1, 3, 5, 7, 9, 11. The set of odd natural numbers. Here we're looking at the set of squares. And here we're looking at okay, so in these examples, I can list all the elements out, right? I just chose to write them in set builder notation. That gives you the impression that we can always list the elements of a set out, but it turns out that that's definitely not the case. And so, but these examples were just to give you some familiar examples to play with set builder notation with. But now let me give you an example where I really need to use set builder notation. There's no way, or at least there's not a good convenient way to list out the elements of the set off the bat. And so here, I want the set of elements of the form n over m, where n and m are integers, but specifically m is not equal to 0. This is the set of rational numbers. I should say that there's a slight technical issue here, which is the way I've written this, it appears that 2 over 4 and 1 over 2 are possibly different elements of this set. So technically, to make this make sense, I have to also say that if you reduce the fraction, so 2 over 4 gets reduced to 1/2, I consider that the same fraction. I'm not going to make a big deal of that right now, but if we wanted to do a careful construction of the rationals, we would have to worry about such a thing. But in any case, we know that, like, for instance, 1/3 is an element of the rationals. We know that -13/5 is an element of the rationals, and 7/8. Right? Just some examples, but basically any fraction is a rational number. That's how we defined it. Also, I've been using this symbol before, but this element of symbol, which looks sort of like an E, is the symbol for saying that a number is a member of a set, right? We've been already using that. What other examples are there? Well, in calculus, multivariable calculus, you often look at a set of elements that can be written as a pair x comma y, where both x and y are real numbers. So it's a set of ordered pairs of real numbers. Another example that you often look at is the unit circle. So then you're talking about the set of elements of r squared, so that x squared plus y squared equals 1. Of course, we call that the unit circle. And we can draw a little picture. If you're inside the xy plane, then the unit circle is this, right? Okay, so those are some examples of sets. And then in calculus and analysis, we often need to deal with intervals. So we might take the interval. The closed interval can be written as the set of all real numbers such that a is less than x is less than b, or the set of real numbers such that a is less than x is less than b. Now we're talking about the open interval, or could have the half open interval like this. Or we could have the half open interval like this. So anyway, we can use set builder notation to define all of these somewhat common and even somewhat familiar perhaps to you sets. Okay, so we've given a lot of different examples. We'll give even more examples as we go along. But now we want to make a definition, something else which is really important when talking about sets. So here's the definition, 3.4. Assume A and B are sets. So if every element of A is also an element of B, then A is a subset of B. And it's really important the way that we denote this. Denoted, A is a subset of B. Okay, so this is extremely foundational and important in when talking about sets. We're going to make claims about sets being subsets all the time. And so we should draw a picture of the idea if you don't already see it. So if B is this bigger set and A is a smaller set inside of it, then that's sort of visualizing the idea of being a subset. We should also try to write this out somewhat more succinctly. So for every X in A, we know X is in B. And if I want to write it even more succinctly, I might say X being in A implies that X is in B. And here, this kind of has the form of an implication on purpose, where maybe I'll use P and Q here since A and B already are being used. So that's like P implies Q. Okay, so you can think of a subset definition as a type of implication that if X is in A and A is a subset of B, then X is in B. Okay, good. Let's look at some simple examples of subsets. So for instance, this set 1, 3, 5 is a subset of the set 1, 2, 3, 4, 5, 6. Okay, no problem. That's because 1, 3, and 5 are contained in the bigger set. Similarly, the natural numbers are a subset of the integers, which is a subset of the rationals, which is a subset of the real numbers, which is a subset of the complex numbers. In this class, I didn't define complex numbers yet, so that's a little bit unfair, but let me just define it for you using set builder notation, right? So it's a set of all numbers of the form A plus BI, where A and B are real numbers, and I is equal to the square root of -1. Okay, anyway, these sets of numbers cover most classes that you're going to take at Lehman. The natural numbers are studied in number theory. All these sets are studied in abstract algebra for their algebraic properties. The real numbers are studied in calculus and analysis. The complex numbers are studied in complex analysis. And eventually these things show up all over the place, depending on the field. But so anyway, that's the subset relationship there. And to give you a non-example, if you will, if I take the set A, B, C, this is not a subset of A, C, D, E, because B is not in the second set. By the way, in mathematics, whenever you put a slash through a symbol, it always means not that thing. So that means it's not a subset when I put a slash through it, right? And then a silly example, if you will, is that the empty set is considered a subset of A for any set. And that's because the empty set doesn't contain any elements. So it's sort of what we say vacuously true. So since there's no elements in the empty set, any element in the empty set is in A because there's nothing to check. Right? Okay, not a huge deal. I don't want to spend a lot of time thinking about that, but it is the case. Um, let's make a note about notation here. Well, first of all, if you say that two sets are equal, then that means that A must be a subset of B and B must be a subset of A. In some of the later videos, you'll see that this is a strategy that we're going to use when we want to show two sets are equal. We're going to show that they are subsets of each other. For now, I'm just making a note of that fact. Let me also say, though, that if A is a subset of B, and you want to be more specific, say that it can't actually be the same, then A is a proper subset, and we denote that a subset like this. Now, I do want to make a little word of caution, which is that subset notation changes depending on what book you're reading and what professor you have. So actually, this is not the convention I tend to like, but I'm following the book that I chose. I actually choose to use this notation for the usual subset where it could be equal, and then I have a different notation for not equal. But in any case, this is a notation we're going to use in this class. I just want to caution you that um, notation is not always universally the same throughout all of mathematics, and you just have to kind of get used to it. And when you switch from one book to another, you have to wonder or ask the question, like, what notation is this person using? Okay, just important to think about that. Okay, so we'll prove things are subsets actually in some later videos, but for now, I want to talk about more set operations, so ways we can combine sets together. Okay, so let's start looking at some set operations. Okay, so this is a definition, and there's several set operations. So first of all, we want to look at union. And so that's denoted A, U, B, though it's not really a U in the same sense, but that's the set of all X so that X is in A or X is in B. So you don't have to be in both, just one or the other is fine. Now let's draw a picture before I move on here. So you want to think of the set A as something like this, and the set B as something like this. And the union here is all the elements in either set, right, or both. Okay, a very important operation. And then next, we want to do what's called intersection. So that has the symbol upside down. And now we say it's the set of all X so that X is in A and X is in B. Notice that's a strict or much more strict requirement. So the picture now is, again, we have A, we have B, but now we only want the elements of A and B which are in both. So we're looking at the overlap here. Okay, good. Now, the book likes to point out next that you can actually take as many unions or as many intersections as you want. So if you're told to take the union I equals 1 to n of sets AI, well, that's like asking to take the union of A1 plus the union of A2 plus the union of AN. And as a set in set builder notation, that's the set of all X, so that X is in each AI for, well, sorry, not each, but for some, so it's in one of them. for some natural number between 1 and n. Okay, I won't draw the picture all the way, but if I just had 3 sets, A1, A2, A3, sorry, 3, then the union is everything in any of the sets. Good. And similarly, we can take the intersection I equals 1 to n of finally many sets. There's sort of a, if you can do this for finally many, you can also ask, can I do this for infinitely many? And the answer is going to be yes. I'll show you that actually in some examples just to play around. But now for the intersection, it needs to be in them for all 1 less than I less than n, and I a natural number. So the picture now, if I just draw it for 3 sets, is A1, A2, and A3. I want only the set of elements which are in all 3 of them, right? So it's this overlap here. Okay, but of course I can do this for 4, 5, 6, however many sets. It's just the picture gets a little nuts, so I'm not going to draw it. All right, so let's play around with this with some examples, because the pictures are helpful, but we need to see some examples, and we're not always going to draw things. So let's see what we're talking about. So for instance, what if A is the set of even natural numbers and B is the set of odd natural numbers? Okay, well then A union B and A intersect B. Okay, to be in A union B, you have to be in one of the sets, either an even integer or an an even natural number or an odd natural number. But we know that that's all natural numbers, right? Because the natural numbers are either even or odd. Now, to be in A intersect B, you have to be in both A and B, meaning you have to be an odd natural number and an even natural number, and that's not possible. So there's actually nothing in the intersection. And for us, this is going to be almost always the reason why we use the symbol empty set, is because when we intersect 2 sets, we find that there's nothing left over. That'll be the most common usage of that. Okay, let's look at another example. So let's say A is the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say B is -4, -2, 0, 2, 4. Okay, so then A union B is, well, I get -4, -2 is 0, 1, 2. Should have made this example shorter. Okay, too late. And then A intersect B. So because A union B, you have to be in either B, A or B. So you get all these elements that are either in A or in B. But when I intersect, I have to be in both. So there's only 2. 2 and 4 are the only ones that are in both. Okay, very good. So those are some examples of unions and intersections. Now I want to add some more operations to our list here. So this is definition 3.9. So again, we assume A and B are sets. Then we want to know what it means to take A set minus B. So that's like X, that's how you say that out loud, A set minus B. So you have to be in A and you have to not be in B, okay? So in a picture, if A looks like this and B looks like that, then the set minus is this guy right here. Oops. Set minus is just part of A that is not in B. Okay, cool. Now, next, if A is contained in some U, then U is called a universal set. Let me just say a little bit about this. So what's going to happen is sometimes there's going to be a clear and obvious like universe that we're living inside of, meaning like in calculus, we're almost always working inside the real numbers. So the real numbers would be the universal set in that case. If you're doing number theory, you're almost always working in the natural numbers. And so a lot of times there's like we know the universal set. Like if you're in complex analysis, then it'd be the complex numbers. And so if you know what the universal set is, then we can define something called the complement, which is just to take the universal set and subtract A. Okay, so in a picture, if I imagine the universal set is somehow encompassing everything that I want to think about, and I let A be some set inside my universe, then the complement is just everything else that's not in A. So it's like the opposite. And from that, you might be able to see, but it's really something you need to prove that if you take the complement twice, you get back to the original set. Okay, so now we can play a little bit with some more examples. So let's say A is set 1, 2, 3, 4, 5, and let's say B is the set -3, -1, 2, 4, 6. Now, you might want to pause the video for a second and figure out what these things are equal to first, and then check with what I get. So feel free to pause it here. But if I take A set minus B, I have to take all the elements of A that are not in B. Notice B contains 2 and 4, so I don't have that anymore. And then when I do B set minus A, I should take all the elements of B that are not in A. So now I get -3, I get -1, but I don't get 2 or 4, right? Okay, good. Let's do some examples with complements. So let's say, let's let the integers be the universal set. By the way, I'm going to say it this way in this class, but honestly, most of the time, the universal set will be clear from the class that you're studying. So again, in real analysis, the universal set will be the real numbers. In complex analysis, will be the complex numbers. Okay, and sometimes we'll have to say what the universal set is more clearly than that, but rarely. So, okay, so if again we go back to this example with here I'm doing even and odd integers, then we can notice that A complement is actually B. So if I look at all elements in A and then look for the complement, I'm looking for everything that's not in A. But if you're not an even integer, then you must be an odd integer. So that's B. Similarly, if you do B complement, you get A. Okay. And if you take the integers and subtract the natural numbers, then you get set 0, -1, -2, -3. And if we take the naturals and subtract A, then we just get the odd naturals, which is not B in this case because B is the odd integers. Okay, good. So there's going to be a worksheet where I have you just play around with all these set operations. It's not supposed to be a hard worksheet. It's just to keep you accountable that you've understood these definitions, right? Okay, let's do one more sort of set operation definition, which will be important for examples. So assume, again, that A and B are sets. Then I can take what's called the Cartesian product of these two sets, which is the ordered pair where A is an element of the first set and B is an element of the second set. Okay, now this is something that you're already, one example of this you're already used to, which is the XY plane, which is the set of all x comma y, so that x and y are both real numbers. So that's like the Cartesian product that you're very much familiar with usually in calculus and things. But it turns out we can do this Cartesian product with all kinds of different sets, and we get some important examples by doing that. So for instance, if I want to do the Cartesian product of 1, 2, 3 with the set 5, 6, 7, then I can list out the elements here as set containing 1 comma 5, 1 comma 6, 1 comma 7, 2 comma 5, 2 comma 6, 2 comma 7, and 3 comma 5, 3 comma 6, and 3 comma 7. Okay, just to give you an idea of what's going on here. And then here's another example that you've maybe never played with yet, but you can take the integers cross the integers, something you would do in an abstract algebra class where x and y are both integers. Now this one we can visualize because it's like 0, 0, 1 comma 0, 2 comma 0, and it would continue there. And then, you know, and I'm drawing these dot dot dots to say like it keeps going in all these different directions, but it's can be visualized in the XY plane. Okay. Okay. Just a set of all ordered pairs um, where the ordered pairs are always integers, where the coordinates are always integers, right? And then just to give you another idea that combines a few things here, I can take the Cartesian product of z with the set containing 0 and union that with the Cartesian product of z with the set containing 1. Okay, if I do that, it's like I'm taking the set n comma 0 where n is an integer, and I'm unioning it with the set m comma 1 where m is an integer, and that's the same thing as the set n comma m where n is an integer and m is an element of 0 comma 1. And I can also visualize that one because it's just like 0, 0, blah, blah, blah. And it's like one copy of the integers and then another one on top of it. Yeah, so if you want, it's like this guy is 0 comma 0 and this guy is 0 comma 1. This is 3 comma 0 and this guy is 3 comma 1 and so on and so forth. Okay, I don't want to get too carried away with some of these examples, but it's helpful to see several different things there. And this will be important, especially when we talk about functions, because this will give us some ways of talking about functions from different spaces to different spaces, which can be quite interesting. And just to leave you with an open-ended question here. So I can take the Cartesian product as many times as I want, right? So, which I haven't done yet. Let me do one example before I go a little further with this. So for instance, I can now, oops, different color. I can now also talk about C cross C cross C cross C. What is that? Well, that's the set of all n1, n2, n3. So now instead of an ordered pair, I am talking about a ordered quadruplet where each element is in the integers. Okay, and the kind of open-ended thing I want to leave you with is here's a question. What would happen if we took an infinite Cartesian product of sets? So again, I'm going to leave this completely open-ended, but I'm not going to answer this question, but I just want to remind you that there's always like more things you can do with mathematics. And it turns out that this example is actually important for talking about sizes of infinite sets and in topology. And it's not as it's not just for the fun of it. It's actually useful sometimes. Okay, so that's it for set operations. In the next videos, you'll see me prove two sets are equal and prove various different properties of sets using these operations.